Okay, so let us begin. Welcome everybody to Majorana-Raychaudhuri seminar series. Uh, Today's speaker is Peng Huang from Sun Yat-sen University, China, and he's going to talk about electroweak phase transition dynamics and its cosmological implications.
Oh, thank you, and nice to see you. Yeah, thanks for Dr. Alish's invitation. And today I will introduce our recent work on the electroweak phase transition dynamics, and especially the cosmological implication on dark matter because it has many aspects like biogenesis. But for time limitation, I'll focus on how we can use electroweak phase transition dynamics to produce or make new dark matter production mechanism, like how we make coffee. In the early universe, the phase transition process, they can produce bubbles. The bubble is like the filters. They can help to filter the dark matter, what we wanted. And as a byproduct, they can produce a gravitational wave signal, like the aroma when we're making coffee. So this is based on the recent work with my PhD student. First, I'll introduce the research motivation, why we study this phase transition dynamics. Then I will simply introduce the electroweak phase transition dynamics and the gravitational wave signals in a nutshell. Then we'll discuss three cases. Case one is very simple. Dark matter induced first order transition. Using this example, I'll introduce how to calculate the most essential phase transition dynamics, namely the bubble wall velocity. Then I will using the phase transition dynamics for new dark matter mechanism like the filtered dark matter and the gated and the cuboid dark matter. Lastly, the simple summary and outlook. Why we study phase transition phase instead model, the electroweak phase transition, the QCD phase transition is crossover, not first order. But we have many motivations for new physics. The most important motivation is for dark matter. So, but what's the nature of the dark matter? Nobody knows. And in recent years, we didn't see any expect signal at LC or dark matter direct search. This situation may point us towards either looking for new ideas for how dark matter is produced. Maybe the traditional freeze out or freezing mechanism doesn't work. So today I will talk about the phase transition, how to use phase transition dynamics to produce heavy dark matter. So since WIMP is not so favored, and maybe we can discuss ultralight or heavy dark matter. So, and for this new mechanism, maybe we can use the new detection method like gravitational detections for this new dark matter production process in the early universe. Other motivations from experiments. So the first motivation is from the Higgs observation. The Higgs observation at LC and the second gravitational wave at LIGO initiate a new area of exploring the new physics and especially dark matter by gravitational wave. Maybe from this figure, you can see in the early universe, our universe is in the symmetric phase, and with the expanding of universe, the temperature decrease. Maybe with the new physics, the degenerate minimum occurs. In this case, a first order phase transition may happen, and in this case, the bubble wall you created from the quantum of thermal fluctuation. Within this bubble expansion, many interesting phenomenology happens. One thing is the particle scattering around the bubble wall. In this scenario, either electric biogenesis and dark matter production can be discussed in this process. Another simple effect is the gravitational wave from this bubble expansion. The bubble expansion, they can trigger the turbulence on sound wave. They can produce strong gravitational wave. And the bubble becomes closer and closer and collide, they can also produce gravitational wave. So this Higgs disk and the gravitational wave, they are close related to the Higgs potential, and the Higgs potential from the evolution in the universe, early universe, they are closely related to the binary symmetry of our universe. It's under the dark matter in our universe. So we want to using this dynamic process for the Higgs field to study the cosmological implication. Let's focus on the dark matter. So the phase transition dynamics, there are many parameters to quantify the dynamics. I'll introduce later. The most essential thing is the bubble velocity. It means how the speed of the bubble expansion. So it's closely related to the electric biogenesis. The particles, antiparticle scattering around in front of the bubble wall, it can produce or explain the biosymmetry of our universe. And I'll focus on this. They are also related to a new dark matter production mechanism, maybe the dynamic dark matter and the gravitational wave signals. To test this this cosmological implication, we need precise prediction of the phase transition gravitational signals. This also strongly depends on the precise prediction of the phase transition dynamics. So, and they can also make complementary tests with the future lepton collider. So the phase transition picture is very, very simple and straightforward. So we can understand this even in our quantum mechanics, or more precisely quantum field theory in early universe, to describe or quantify the phase transition, we need to calculate the Helmholtz free energy density. In quantum, from the finite temperature quantum field theory, this effective potential just equals the Helmholtz field free energy density. So it includes three effects: the twin-level potential, quantum correction, and the thermal correction, and they can be unified in this form. This is quantum correction, the log term, and the J function. JF means the thermal correction. Having this Helmholtz effective energy density, we can calculate the quantum tunneling rate. This determines how the bubble creation rate. So how the bubble created during the phase transition process. And very straightforward, the bubble collision, they can provide a gravitational wave. This is very straightforward, just in general relativity, once you have time-dependent quadruple, you have gravitational wave radiation. Before bubble collision, the bubble is spherical symmetry, so there's no quadruple. But after bubble collision, the spherical symmetry is broken, and they can radiate gravitational wave. The quadruple occurs. And because the expansion of the bubbles, they can trigger turbulence and the sound wave. They can produce even stronger gravitational wave. Maybe as people in astrophysics, they are not familiar with this, but it's very generic sources, because we solve the Einstein field equation in FRW matrix, they can have this wave equation for gravitational wave. Once we have anisotropic stress tensor pi ij, we can produce gravitational wave. In general, they can classify into 4 cases. The bubble collision is just the gradient of the scalar field, partial I phi and partial j phi. And for turbulence, is the most simple case is just calculated by the velocity field, the vi vj. they can produce the pi j, and the magnetic turbulence, they have the EI, EJ, electric and the magnetic contribution. When people are discussing the induced gravity from inflation or some PBH model, they have this partial phi and partial psi. This very generic. Before, I think this is all the bubble phase transition gravity is an old idea by Horgan, Vita, and many other nice works. Only after the discovery of Higgs and gravitation with this topic becomes realistic and more testable. And we can simply estimate the frequency of the peak frequency of the phase transitions gravitational signals. We can, because the peak frequency is determined by the characteristic scale of the sources. So roughly the bubble, the mean bubble separation is about 10 to -2 to 10 to -3 of the Hubble side. So we use this quantify the size L over the Hubble scale to quantify this. And then we consider the redshift. So we have this formula. When, for example, when the temperature is about 100 G, it's about millihertz. So for electrical phase transition, the peak frequency is just around millihertz and detectable by this Tianqi Taiji. For QCD phase transition, the temperature is about 100 meg eV. So the peak frequency is around nanohertz. So now focus on the phase transition dynamics. The first, how we calculate the phase transition. The most simple quantity is the phase transition strength alpha and the phase transition temperature and the mean bubble separation. But this strongly depends on how precise we calculate the finite temperature effect potential. There are many problems like the day series summation problem, the gauge dependence problem. Maybe you can see Michael's works, and also there's for the base calculation problem. Yeah, today I will cover these topics, but focus on this more dynamical parameters, what's the speed for the bubble wall. Because this is the most important parameters either for the physics or for the signals. The other parameter is energy budget. They quantify how much of energy converted to gravitational wave signals. The energy budget also depends on the bubble velocity. So we are focused on this because from the aspects of cosmology, this bubble velocity is most essential for the electrical band gases. In theory, the electrical band gases favor a small value of bubble velocity to guarantee a sufficient diffusion process. And for dark matter production mechanism, this dark matter density is directly related to the bubble velocity. And for gravitational wave signals, the spectrum or the signal is very sensitive to the wall velocity, bubble velocity. And the recent work we find that not just as many, I think it's straightforward. And if we observe the phase transition gravitation, I think in most cases, the bubble velocity would be the first parameter to be determined from the data. Even though from the aspects of experiment, the stochastic gravitational wave is not easy to detect. And I think from roughly from 2020, there are many nice works to discuss the friction force during the bubble expansion or direct calculate the bubble velocity. and also recently many works on the energy budget. These two parameters are essential for the precise calculation of the phase transition gravitational wave. As example, how in our early work, maybe 7 years ago, we discussed a dark matter and biogenesis model, maybe more precise, asymmetry dark matter model, how by a cosmological phase transition. In this case, you can see the dark matter density is significantly depends on the bubble velocity. So this means we must precisely calculate the bubble velocity. And from this figure, we show an example how the gravitational wave is sensitive to all velocity. For example, given the same phase transition parameter, this black line represents the case for bubble velocity equals point line, and this dashed line represents the spectrum for bubble velocity equals 0.1. You can see their strength of gravitational wave is significantly different. So they have several orders difference. So for the high or large bubbles, they are detectable by LISA and tensing, but for all velocity around 0.1, it's difficult to be detected by by LISA. Okay. So we must precisely calculate this all velocity. For the energy budget also depends why this gravitational wave is so sensitive to the all velocity. Because one reason is the signal is proportional to the energy budget kappa. So you can see the kappa is also depends on the bubble velocity. But I think before 2020, most of the paper discussing the phase transition physics, they usually put this. They don't calculate this. This all. They just take it to the input parameter. Yeah, there's some parallel work by Guy Moore, and they calculate this in standard model like model in 1990s around. But later, few people to discuss how we calculate this all velocity. So I'll take a simple model to show how to precisely calculate the bubble velocity. By simple extension of a standard model, like Euler doublet model, I think this is the most simple case. We extend the standard model with the Euler doublet. This model, they can provide lateral document candidate and produce strong first order transition and gravitational wave. Yeah. This is simple. The difficult thing is, even for me, when I first calculate the gravitational wave many years ago, I also didn't calculate the bubble velocity and put it by hand. But last year, and my students, they will calculate this all velocity in this model precisely. The idea is where the process is very straightforward. First, we need to get the equation of motion for the Higgs field in the early universe. Yeah. In the planar approximation, we can appears bubble velocity appears here. The partial z's from this. Because to solve this equation for after we solve this equation, we can get the all velocity, bubble velocity. But the problem is how we get this term. So this term is the effective potential we can calculate it from the standard approach using the quantum temperature field theory. But how there's an additional term. This is the so-called friction term. This means when a massive particle passing through the ores, they can produce friction force. It's like friction force, because when a massive particle enter enter into the broken phase through the bubble wall, they suddenly obtain a mass. So they feel like they produce friction force. So this friction force is only determined is proportional to the perturbation of the distribution function for massive particles. You see, because if you can see from here, only massive particles contribute to the friction force. So the key point is to calculate the perturbation of the distribution function for each massive particles. In standard model, we have a top quark, W and Z boson, maybe Higgs boson. So if you add a new elect doublet, you have more new species. You can so for each species, each massive particle, we should obtain the perturbation. So how we calculate the perturbation? The standard approach is solving this perturbation distribution by solving the Boltzmann equation. We're using perturbation method. So the Boltzmann equation df/dt equals ct. So we write the df/dt split into equilibrium term and the perturbation, and we write it in terms of the all losses. It's like in this term, and so left thing is calculating the collision term. The collision term can be calculated by calculating the scattering amplitude when the particles hitting or scattering in the vicinity of the bubble walls. This is also difficult, and the most difficult thing is this equation is also difficult to solve. We need to use some tricks. So here we use some traditional flow ansatz. We take some reasonable flow ansatz. So we using the truncation scheme, we truncate this equation to 4 equations, and then we solve this equation and get the perturbation and substitute this back into the equation of motion for the Higgs field. Then we can obtain the bubble velocity and all cycles simultaneously. So more technically, we show how we calculate this in this figure. I will skip the details. And the model is, just mentioned, is very simple, just well-studied elect doublet model. It's published last year with my PhD student. We start from to get the equation of motion. One approach is just from the tensor momentum conservation. The first contribution is the scalar field, is the traditional case. And using the conservation condition, we have this equation. This is the friction force, as I mentioned before. So the key point is to obtain this delta Fi. I is for each massive species. How to calculate this delta Fi in the blue color. So this is standard in a WKB approximation. This df is equals partial t and z dot partial z and pz dot partial p dot. Just we notice that the pz dot is proportional to the mass scale derivative to the position. So this term it behaves as an external force from the bubble. So this is the in the literature called a source term for the bubble or for the friction force. So we permit to disturb this distribution function like this, and taking the reasonable flow ansatz, we have the chemical, potential, temperature. We have delta T and delta T. Background is we take all the light particles contribution into the background. They share the same temperature and all velocity. So we having this, then we just solve this equation, and we're using truncation scheme. First, we integrate over momentum. In the other case, we integrate with the momentum pz, we time pz and integrate over p, and then we time e energy and integrate. So we integrate this by 3 cases and obtain 3 different equations. And for background, yeah, we have similar. So combine this together. Before that, we still need to calculate the source term. So without the new physics, we just have top quark contribution. The gauge boson, this W means W boson and Z boson together. And here we assume benchmark point is the dual scalar. We also assume they share the same mass. So it's consistent with our benchmark point. So we have more collision terms. Having this collision term, this when do this numerically, so Monte Carlo's integration. So it's temperature dependent. This because this collision term, we use this gamma symbol to represent the collision term. The numerically we solve these perturbations for each species for each species, the mu, the top quark, W by Green function method. This is having this perturbation. The final equation of motion for the Higgs field is like this. The Higgs two derivative, and this we have this perturbation already. And this equation is also difficult to solve. One trick is we use the physical condition. We integrate this by the time this with phi prime this and integrate the equation. This means the pressure difference is 0. And the second equation, it means the wall thickness is fixed when the bubble wall is stable. So combine it with numerifying the all velocity is the right point. This means we obtain the precise value of the all velocity and the all thickness simultaneous. So having this precise value of bubble velocity, we can precisely calculate the phase transition dynamics and the gravitational wave. And if we use this process to discuss dark matter or biogenesis, it's also more reliable because dark matter and the phase transition gravitation is sensitive to the all velocity. So we move to another case is really dynamical dark matter production mechanism, or the so-called Kubo dark matter. Yeah, it's like this idea is I think maybe original is from Witten's Cook-Luggage, and maybe 10 or more than 10 years, Rubakov, they write a paper on the Kubo dark matter. So later in 2017, we write a paper on this to propose a simple model to realize this. We assume the dark matter candidate chi is it has mass is proportional to the a phase transition field ice. So, and we require the mass of the chi field is much larger than the phase transition temperature. So this chi field, the dark matter is difficult to enter into the forced vacuum. So in this case, this bubble wall is like the filter. So we choose the good coffee beans. So we use the filter to get only the big or heavy coffee beans. So the same case, the bubble wall just filter the the dark matter candidate in the force vacuum. So, and later with the expansion of the true vacuum, yeah, this dark matter, they form the so-called QUBO, and gradually shrink, yeah, form the reliable dark matter candidate. So uh, in this case, you can easily see this dark matter density is sensitive to the all velocity. So we find that by simple estimation, we obtain the relationship of the dark matter density with the all velocity and the baryon to photon ratio, and then the nucleation rate. So you can see that this QUBO dark matter or asymmetry dark matter is sensitive to the phase transition dynamics, like the all velocity. So in this paper, we only consider the global QUBO case. Recently, we generalized this gauge QUBO to the global QUBO to gauged QUBO. It's more general cases. Yeah, but we'll skip the details. It's the same idea, just to include the gauge field. Okay. This paper we explicitly check the stability of the QUBO, gauged QUBO, and precisely calculate the phase transition signal, gradient signals. The last case is the so-called filter dark matter. I think this name is given by Kim's and Juno and the Baker's paper. They have this, they name it with a fancy name, filter dark matter. This is opposite case. The bubble walls still in the phase transition. They are like the filter, but they only filter only the dark matter enter into the ore, or the force, the true outcome becomes the dark matter. So more precisely, when the dark matter candidate, the scattering or moving towards the bubble ore, only the particles with very high energies, they can enter into they can penetrate the bubble ore and enter into the broken phase, and finally becomes a dark matter density. Only the key point of that is only a small fraction of the particle candidate, the dark matter candidate, can enter into the true vacuum, and this is very important. So in this case, is also straightforward to say that this dark matter density is also sensitive to all velocity. So there are many new works in this field because this filter dark matter really provides new mechanics for dark matter production, especially for heavy dark matter, because for traditional freeze-out mechanics, there's unitarity problem for heavy dark matter, but in this case, there are no such constraint. This is the two papers by Van Pervens, Kim, and this work from IBS. So later, many new studies under this using the phase cosmological phase transition dynamics. And in this case, but most of the work are great ideas, and because we notice that because this dark matter density is very sensitive to the phase transition dynamics, so we must carefully discuss all the dynamic parameter like the velocity profile and temperature profile, because it's easy to imagine that the closer to the bubble ore, the temperature is much higher because of the reheating kind of heating effects. So in this work, we precisely calculate the hydrodynamical effects and to precisely get the velocity profile, temperature profile in front of the wall. Because in this filter scenario or the dark matter density really sensitive to this temperature and the velocity distribution. The same as before, we using this is the traditional point, and this is the profile equation from the large moment conservation. So we just include the every necessary effects. And for this real standard toy model, we consider two cases or three cases. One is the hybrid, one is the detonation case, one is the deflagration risk. This is the hydrodynamic part. The other part is because we must discuss this with collision term. So for the collision term calculation, we must include concrete interaction term in Lagrangian. This is also standard. So we just show the final results. So we show the radical density and the relationship with the dark matter field, the temperature dependent dark matter mass over the temperature is the so-called Washout parameter. So without, for example, without for all velocity equals 0.01, without heating, we can get some analytical approximation is the dashed blue lines, and we can also more precise, we get numerical result is the blue lines. In this, both the blue line, we didn't consider the heating effects in front of the bubble wall. But if we consider the heating effects due to the particle scattering in front of the wall, the radical density is significantly changed to the right lines.
Hi, we have 5 minutes left.
Okay, it's almost done. Okay, thank you. And for the detonation case, it's more significantly for the heating effects. So this will also significantly affect the gravitational signals for the same benchmark point. Yeah. So I'll just give a simple summary. The bubble wall during a first order phase transition, this is the key phase transition dynamical parameters. They can be a lateral filter to study the dark matter production mechanism. The byproduct, this dark matter mechanism can be naturally easily detected by gravitational wave signals. Thank you.
Okay, thank you for the nice talk. We have some time for question answer.